Okay, so this is a little video that should help maybe with your post-lab calculations for the heat of vaporization lab with Dr. Weatherman and Dr. Mottel. Okay, so let's look at what we have. So what we have recorded is the masses of the device plus the alcohol, the device plus the alcohol in the bubble. We also know the density of our alcohol. If we don't know that, we can look that up. And then you have your various temperatures and the meniscus readings. Okay, so you could use all that. That's what we have. Okay, so now let's look at what we want, what we need to have. So we want to basically fill out the rest of this table. Well, that first row, the temperature, that's pretty straightforward. Meniscus readings, we can do that as well. So what we need to get then is the volume of the bubble at each of these different temperatures, the volume of the air, and then the volume of the vapor. Once we know the volume of the vapor, then we can get the partial pressure of the vapor, which is what we need then for the graph. So let's turn to the first thing that we need to do, which is the volume of the bubble there at room temperature. Okay, so to figure out that first volume bubble, we need to go back to those mass differences. So the difference in the device after it has the bubble added. So that difference then is a mass, which you can convert to volume by just dividing by the density of the alcohol. Okay, and that will give us that first bubble volume. And then we can figure out the vapor pressures after we do a couple more manipulations. Okay, so that first temperature then, we'll know our initial bubble volume by doing the density and the mass difference. And then we know the volume of the air, which was 200 microliters. So we can subtract that, and that will give us the volume of the vapor at that first temperature. So that yellow box there will have the answer. It'll be in microliters. It should be a relatively small number, and so we can go from there. So now we need to figure out the bubble volume at all the other temperatures, okay, that blue box there in the table. And so we can do that by simply taking that initial bubble volume that we did at room temperature and then adding whatever volume increased, which we should be able to get from the meniscus reading. So if we take that initial meniscus reading and then we have that final meniscus reading at each temperature and then just add that to the initial bubble volume, you'll get the volume of the bubble. Now, the volume of the air is not 200 microliters at these other temperatures because it's going to change due to the temperature change. Okay, so we need to calculate that. Okay, so we can just go back to the gas law. Okay, so pressure and number of moles and R are going to be constant. So really we're looking at variations between V and T, right? So this is Charles' law. And so we can take that 200 microliters as our initial volume, and we know our initial temperature, which is at room temperature, and then the final temperature, T2 then, would be the temperature of whatever data point you're reading. Okay, so that's going to get bigger, assuming that your temperature goes up as you go along. And so now you'll have the bubble volume at each temperature, which is the blue box. You'll have the volume of the air, which will be the pink box. And so the difference then is the volume of the vapor at each temperature, which is the orange box. Okay, so that's easy to do in Excel. You can get all those numbers. And once you have all those numbers, then it's a relatively straightforward transformation to get it to vapor pressure. Because vapor pressure is really just partial pressure of vapor. Okay, so we can get that from the fraction, and we can get a fraction from the fraction of the vapor in that whole bubble by just taking the volume of the vapor and dividing by the volume of the bubble. That'll give us a fraction. Multiply that times atmospheric pressure, which should be the thing that's affecting the bubble when we put it in there, the air bubble. So, and that will get us then the vapor pressure. Okay, so then it's just a matter of fact of making the graph. Make sure we're using Kelvin, and make sure you put in the units. You got to do the natural log, so log base E. For those who don't remember what natural log is, you have 1 over T. Make sure you put in a title, axis labels. Those are always handy. And then you should be able to take that slope, determine the enthalpy of vaporization, which will remember that the R is the thermodynamic, 8.314 joules per mole Kelvin, and you can convert it to kilojoules per mole in the final calculation.